Right, perfect. I think people are still joining, but I start with the introduction. So welcome everyone to our first talk of this year of our data-driven methods in engineering and science seminar hosted by the Kutz and Brunton group. We are really excited to have Laure Zanna today, who is going to talk about advances and challenges in data-driven turbulence closures for ocean and climate models. Laure is a professor in mathematics and atmosphere and ocean science at the Courant Institute at NYU. Her research focuses on the dynamics of the climate systems, and the main emphasis of her work is to study the influence of the ocean on local and global scales. Prior to NYU, she was a faculty member at the University of Oxford until 2019, and obtained her PhD in 2009 in climate dynamics from Harvard University. Today, Laure will talk about data-driven turbulence closures for ocean and climate models. And during the talk, you can ask questions in the chat, and you can also raise your hand so we can unmute you as soon as we open the floor for questions after the talk, or in case, depends on you, Laure, if you want to have like question between the talk, you could just say that. Okay, so perfect. So thank you very much, Laure, again, for being with us today, and you can take it away.
Great, thank you very much for the invite, and thanks everybody for joining. So yes, please ask questions during. It's a lot more fun. It's never as much fun as being in person, but it's kind of the best we can do right now, and it's great because we can get people from everywhere. So I'm definitely very excited about being here. So yeah, so again, thanks again for the invite, and as Urban mentioned, so I'm going to talk about data-driven turbulence closures, and I'm a climate dynamicist, right? So kind of start with that little piece of introduction, as my background is really trying to understand how the climate system works, and really how can we best model the climate, and how can we best come up with prediction into the future. So let me kind of play that movie again a little bit. So I'm a climate dynamicist that focusing on the ocean. And here what you can see is a simulation. So a climate model simulation that is run at 1/10 of a degree resolution. So that means about a 10 kilometer by 10 kilometer horizontal grid. And what we're going to concentrate on today is trying to come up with closures for those kind of filaments and features that have scale of about 10 to 100 kilometers roughly. So that's really going to be the topic of today's talk. So when you want to model the climate, there's a lot of excitement because it's a complex system, but that also means it's a hard task, right? So you need to get the fluid dynamics right. You need to have radiative transfer in the atmosphere. You need, atmospheric chemistry. In the ocean, you need biogeochemistry. That means, how the carbon cycle evolves. You also need to model land. So you have many components that are interacting with one another. And you also have, again, many scales interacting with one another. If we take the oceans just for a second, right? So those are governing equations for the ocean. So momentum is on top. So we basically have, rate of change or Navier-Stokes on the sphere, on the rotating sphere. So, lots of forces and a lot of components. Next equation is conservation of mass, basically kind of thermodynamics. So rho is density here. We also have an equation of states, and that's kind of a fun fact for the ocean is we don't really have a good equation of states. We know it depends on temperature, salinity, and pressure, but we don't have good relationship like we do in the atmosphere where we can use the ideal gas law. And then again, we have basically additional equations for temperature and salt in the ocean. So basically, again, thermodynamics equations that gonna advect, meaning gonna transport heat and salt and mix it, and also gonna have sources and sinks from the atmosphere. So heat fluxes at the surface of the ocean, but also evaporation and precipitation are gonna change the salt content. So highly nonlinear, highly complex equations. That's just for the ocean, right? So try to add all the other components. So if we assume that those equations that I just wrote here apply to each air or water parcel just for a minute, and we assume that we have about one meter cube of seawater that evolves independently, meaning every single grid cell will evolve independently from one another. So you would need to actually have basically 10 to the 28 equation to solve. That's just for the ocean dynamics. So it's a massive number of equations, right? So obviously, what we do is we're going to break those equations, right, into pieces to actually solve them numerically on the computer. And so again, you're basically going to solve all those equations on the grid. And the typical grid of a climate model nowadays is about 100 kilometer by 100 kilometer. I'll show you what it looks like in a second. And so that also means that everything that is happening below the grid box size of the climate model that we're using is actually not resolved. So again, let's look at that simulation again, but now with a little bit of a sense of scale. So simulation from a coupled climate model run in Princeton GFDL. So it's one of the big climate center. New York City for scale. And that's one of the high resolution simulations that we have. So it's about 10 kilometer by 10 kilometer. So basically 0.1 degree by 0.1 degree horizontally. And you can see those very nice filament structure. Here we're looking at the temperature of the ocean surface in that simulation. So that's the Gulf Stream, so very strong currents that is driven by the wind, but also by those turbulent features that are detaching and then re-injecting momentum and energy into the flow, strengthening it. And so those kind of features, those mesoscale features over here, again, about 10 to 100 kilometers can only be resolved if your resolution is higher than that 10 kilometers. So let's compare 3 different horizontal resolution of the climate model. So we're going to continue looking at this field of surface temperature of the ocean, the same climate model. So basically, you're solving pretty much the same equations, but you're solving them on different grid size. So on the left, it's going to be pretty much a typical climate model today, 100 kilometer by 100 kilometer grid box size. In the middle, that's where we're getting nowadays and where we're probably going to be for quite a few years. So we call it about a quarter of a degree or something like this. So it's going to be about 40 kilometer by 40 kilometer horizontally. And then on the right is the very pretty simulation I showed you before, which is about 10 kilometer by 10 kilometer. And that's super expensive. So we have a few of those, but it's not something that you can typically run, for 100 of years and things where you're going to do projections with. It's actually computationally expensive. So you can already see, right, that it's very, very blurry when you're on the left because you're very close resolution. It gets better when you're in the middle. You get more structures, and of course, the filaments and the structure and the turbulence that you get at 10 degrees increase. And so let's just run the movie to show you. You have a rather laminar and viscous fluid at 100 kilometer resolution horizontally. You do better as you increase resolution, and of course, much better if you can resolve all the scales. But again, computational expense usually prohibit us to run climate simulations for a long time at that resolution. So what does that mean? Well, of course, you get prettier movie if you run at high resolution. But again, the key aspect here is those turbulent features that we don't resolve are important for mixing heat, tracer, the interfacing between the ocean, the ice, and the atmosphere. So they have a pretty large impact on ocean currents, how much heat we're going to take up, and so on and so forth. So it's definitely kind of important to resolve them, not just because, again, we get more turbulence, but because the turbulence impacts the large scale flow and impacts the large scale climate dynamics. So because of this lack of resolution and those processes that we can't resolve that are too small compared to the grid box size of a climate model, projections and climate models in general are uncertain, right? Is that we're missing some processes here. And so I talked about ocean turbulence, but there are many other processes that are not well resolved in climate models. Clouds is one, obviously, right? So the scales are much smaller than the grid box size of a climate model. Gravity waves, or basically non-Newtonian stresses in the ice components. And again, I talked about ocean turbulence already. So that's one reason climate models have biases, have errors, and why projections are uncertain. It's because we're missing some key processes that are too small to be resolved. The second reason why models or numerical simulations have errors and why it will, to some extent, deteriorate some of the climate projections we're thinking about is numerics, right? We talked about having those nice continuous equations, but we need to break them down to solve them on a grid and basically integrate our numerical model forwards. So everything that is below that grid is not resolved. And so that was this kind of first error. But the second thing is we need to approximate those continuous derivative into discrete derivatives, right? So basically the numerics and the approximation on the grid will be another source of error. So we have two basically main errors that are entering climate projections overall. So I'm mostly going to focus on those kind of subgrid scale, those smaller scales that are not resolved in climate model, but I'm going to touch upon the discretization and the numerics towards the end, because I do think there's an important interplay. And I think that's some of the, I guess that's some of the lessons that we've learned over time. So the term closures and the term parameterization, I'm going to use them, towards this talk, and they're basically the same. So what do I mean by that? We already talked about all those processes that are not well resolved, clouds and so on in the atmosphere, turbulence and mixing in the ocean. So typically the way we've dealt with that was saying, well, let's try to come up with a simple idealized representation of those processes that are too small. So we can think, let's take mixing, for example. Usually what we're going to try to do is to come up with a mathematical relationship that's going to mimic the influence of those small scale onto the large scale. So for mixing, you could say, well, the turbulent features are going to steer and mix around. And at the end of the day, all you're going to do is basically dissipate, either momentum or dissipate tracer like heat or so on and so forth. So basically, you're going to build a mathematical expression that could be the Laplacian of momentum with some coefficient in front of it, and that will mimic the effect of mixing onto the large scale fluid. And so mathematically, it will look something like this. You will have basically a force or a rate of change of momentum due to mixing that's going to be equal to some functional form that depends only on the coarse resolution variables that you have, right? Because we know nothing about what's happening below the grid box size. So the goal of the parameterization of the closure or the game is to come up with a simple idealized representation of those processes only as a function of the coarse resolution variables. And we've been doing that for decades in climate models and obviously in many other applications in physics as well. But the problem is, again, our simulations still have errors, and those errors are due in part, in great part, to those parameterization. There's still plenty of errors because we put a lot of assumptions when we build it. So what we've been doing for the last few years, and again, I know this group has been working a lot on the turbulence closure, or thinking a lot about the turbulence closure from a data-driven perspective, especially for turbulence and 2D fluids. We've been thinking about this, but for larger scale. So those kind of mesoscale features that are 10 to 100 kilometers and influence the climate. So can we use data and machine learning to actually improve climate model by learning better representation of those small scale processes? So you need data like everything else, right? So we basically need to find a lot of data. So I showed you that we do have some simulations that are relatively high resolution. We have a few of them, we don't have tons of them, but so globally we have a few and they're pretty good quality. And we can run also idealized domain simulations. So basically, ones that you can actually run at very high resolution, but in a smaller domain. So you can get basically it's not as expensive as running a global model. And using those data sets plus machine learning and hopefully some kind of physics embedded in it, and I'll tell you a little bit about this, we can come up with a new representation for those subgrid scale processes without any a priori, without us making an assumption about the mathematical form of those subgrid processes and how they influence the climate. So there's been a lot of ideas out there and a lot of people kind of thinking about this, both for atmospheric processes and ocean processes. So as I said, for the atmosphere, clouds and convection, so basically deep convection, where you see those kind of very deep and tall clouds are pretty important for climate. So there's been a lot of papers on that, but it goes back actually more than a decade ago, looking at radiations, for example. And in the recent years, the number of papers is literally exploding in terms of kind of finding new representation of atmospheric processes. In the ocean, there are few studies out there. So our group has definitely been quite involved in the last few years with this kind of mesoscale turbulence. There are additional papers that are coming out, especially about vertical mixing. So how much do you mix vertically in the ocean columns? So lots of exciting work, lots of exciting opportunities, but plenty to discover. So what I'm going to do here in this talk is I'm going to focus on those kind of mesoscale closures. And I'm going to show you some of the work that we've done and some of the challenges that we're facing, and where I do see opportunities, but also where we took a step back and try to reframe our questions or our problems to try to actually make advances that could continue for a long time, rather than just having one paper at a time with one more new result, which is always exciting, don't get me wrong. But I think there's a lot to learn, and I think we kind of taking a step back a little bit and trying to rethink how we could best combine physics data and machine learning for climate modeling. All right, so same picture as before a little bit, but kind of now it's flipped around. So we're looking at surface currents in the ocean. And so again, high resolution, intermediate resolution in the middle, coarse resolution on the right. So again, a very laminar flow on the right compared to a very turbulent one on the left. So the turbulent one is where we resolve all those mesoscale features, and you can see those strong currents. So what we're going to do is we're going to take data from those very high resolution simulation. We're going to filter them or coarse grain them, and we're going to extract the missing forcing, so the missing force that we want to put on the right-hand side of this coarse resolution climate model to make him behave the same way as a high resolution. Now, I just kind of make, I'm going to pause for a second. We're not trying to do super resolution, right? So I'm not trying to make this image look like this one. We continue running at coarse resolution. We're just adding a term on the right-hand side of a model that is solved at coarse resolution, where that term represents the effect of turbulence onto the large scale flow. So we'll always be running our climate simulation at those coarser resolution simulation, at those coarser resolution ones. Okay, so why mesoscale? Well, as I said before, they're pretty important for mixing and steering of momentum and tracers in the ocean. And from a fluid perspective, we're not in a three-dimensional Kolmogorov type turbulence here. The ocean is highly stratified, so you can think about basically each layer of fluid being, basically almost a quasi 2D flow. And so that means there is a pretty big potential for an inverse cascade or backscatter, meaning that if you resolve those turbulent scales, what they do is they take energy from the small scale at which they're resolved, and they basically feed it to the large scale. So you can take momentum and energy from the small scale and feed it into the large scale flow. So you can energize your flow like this. And that's why we get some stronger currents, and that's why the ocean dynamics is actually heavily influenced by those turbulent features, that they're not just little dissipating features that actually kind of upscale energy and momentum back up. So that's why they're pretty critical. So, mathematically, they look something like this, basically. So that would be a turbulence closure that you can diagnose from a high resolution simulation. The U's are the velocities in the zonal direction, and the V's in the meridional direction. So what I mean is U is in the X direction, V in the Y direction. And we're going to assume that we're doing that for each layer of the fluids. Okay, so as I said, we're going to use data and we're going to use machine learning without any a priori assumption about the mathematical form of our expression to come up with a parameterization or a closure for ocean turbulence at the mesoscale. So this started with actually my former PhD student back when I was still in Oxford, so Tom Bolton, and then continued with Arthur Guillaumin, who was a postdoc with me at NYU and now is a new faculty back in the UK. So we took data from high resolution simulations and used convolutional neural nets to learn a new subgrid parameterization for ocean turbulence, so a new closure for ocean turbulence. So we started with, some of the, basic thing with idealized simulations and only use in our loss function a mean square error. But recently we tried to, think about it a little bit different. Any of those closures that we're learning, doesn't really matter how we do it, from data or from physics, they're still uncertain because I'm learning a nonlinear mapping between velocity and a highly nonlinear turbulent stress, right? In something that is already filtered and coarse grained. So rather than trying to learn only one value of the subgrid forcing at every grid cell, we decided to change the loss function and make a little assumption in it by assuming that it was basically a normal distribution with mean and standard deviation. So what we've done is we literally changed the loss function to a log likelihood with a normal distribution, so we could learn the mean and the standard deviation at every grid cell. So what we do, we take as input a velocity field, so coarse-grained velocity field from a high-resolution run. We only took a few places, actually, rather than take the whole domain. Mostly it's a lot of data, and we didn't really need it. So a few regions for which we pick basically the velocity as input, and output, we ask it to learn the subgrid forcing, again, at every grid cell on a coarse resolution grid, but we ask it to learn both the mean and the standard deviation, assuming that I have basically a Gaussian distribution for the subgrid tendency. So we're learning a conditional probability of the subgrid forcing onto the velocity, assuming that that conditional probability is Gaussian. So as always, right, you need to figure out if you're doing a good job or a bad job. So what we've done is we took data from a simulation that was run with a fixed CO2 concentration. So what do I mean by that is when we run climate simulations, we have to prescribe some amount of carbon dioxide that we put in the atmosphere. And so the reference simulation that we like to use is called the pre-industrial control, in which the concentration of CO2 is 280 part per million. It's kept constant. And so we took the data from those simulations, kind of split it, right? So we trained and validated on one piece of the data, and we tested it on some remaining data. And we showed that it did a very good job. Now, what we wanted to do was, okay, if I learn a turbulence closure on a given data set, but I want to use my climate simulation not just to simulate present day climate, I also wanted to simulate the future, right? That's a whole game to some extent, is I want to be able to model the climate, but I want to make better prediction. That means that all the turbulence closure that I'm going to add also need to work when I increase CO2 into the future. So we did another test in which now we tested our resulting, learned neural nets on data from a warmer climate in which the CO2 was increased by 1% up to doubling and then quadrupling. And this is the R squared for our learn subgrid turbulence closure in this case. And so basically what you can see, so blue is 50% scale, right? And so 100% scale is when you go to the kind of first darker maroon type colors. So in most region, even though our simulation, our data never actually included some of those warmer worlds, some of those warmer climates, we're still doing a pretty good job, right? So I mean, even in places where it does poorly, it still has some decent skill. So what does that tell us? Well, it tells us that for turbulence closure, at least data from a control simulation in which the CO2 was lower than what it might be, or probably will be, and very likely will be, and continue to be, is still enough, right? But it's not enough in some region. And so I can highlight a few places where it does a poor job. High latitude. And in high latitude, it's where you interact with ice, especially sea ice. And there, the interaction between our ocean turbulence and the non-Newtonian parameterized sea ice is quite different. And so the fact that the algorithm never seen any of those data sets showed rather deteriorating skills in places where I never seen the data. So the good news is we can generalize quite well to different climate. The bad news, which is kind of obvious, right? There are some interactions, not just amongst scales, but amongst components that unless you give it to your algorithm, you will never catch it. And so that's kind of the disadvantage to some extent, is you need to make sure you have data from all the interaction of all the components. So by the way, I don't know if there are questions or anything, but I'm quite happy to take them. I can pause for a second if necessary.
Yeah, there are two questions in the chat.
Oh yeah, please go ahead.
Maybe
yeah, sorry, I'm not monitoring the chat, so I can't let you.
So Lucian asked, can you also provide a sense of the computational resources used for getting solutions on these grids? I think he posted the question when we were talking about the 10 and the 100 kilometer grid scale.
Yeah, absolutely. So usually the global simulation that I showed you is not something that we can run ourselves, right? So those are run on, basically HPC of climate modeling centers, and they basically can take months until you get them. So the computational expense is definitely high and not something we can do ourselves. So it's really a big machinery of the climate modeling centers that can run those simulations.
Okay, then we have a second question from Melody. How do you choose regions for machine learning?
Yeah, so I guess in the input data, was it the, I hope.
So yes.
Okay, yeah. So here it was a little bit of intuition. We picked 4 regions where basically the scale interaction was different. So in those regions of the Gulf Stream extension, for example, the type of turbulence is different than in the equator, where the Coriolis parameter, which is basically an indication of rotation, the fact that we're on a rotating planet, is quite different. So we basically try to pick regions where the scale interactions were different. We've done new tests where we took completely different regions or where we took the entire globe. Doesn't make a huge difference as long as you have enough variety and as long as you pick out the regions where most of the turbulence is happening.
We just got another question in terms of computational resources from Bob. So parallel question mark, how many processors, MPI?
Yeah, all right. So that will vastly depend, right, on the machine that you have. And again, will depend on the resolution that you have. But yes, we're talking about massive resources.
And maybe the last question before we continue from June, if the cells are assumed to evolve independently, where does the coupling between cells come from?
Okay, so in the climate model, there is definitely an interaction between cells, right? So you can think about every single grid cell next to each other actually talking to one another because there is transport. So, advection, which is basically the velocity times the gradient between the tracer, is going to be basically a connection between the cell. Mixing is going to be a wider stencil. So there is definitely connection between each grid cell in a climate simulation.
Perfect. So that's the question for now. So let's just continue. Thanks. And yeah, I invite you to just post the questions in the chat so we can have these like intermediate Q&As.
Yes, and I'll try to pose. And if I don't, feel free to unmute yourself and tell me to take question. I definitely happy with that.
Awesome.
Great. Okay. So that was the good news for the neural nets. Just one little additional piece is by learning the mean and the standard deviation in those simulations, you have some kind of measure of uncertainty. Of course, it depends on the probability distribution that you choose, right, to actually embed within your loss function. But that means, nonetheless, in our case, the approximation was not terrible. It's not perfect, but it wasn't terrible. We could actually have some kind of measure of confidence interval. So here, what I'm plotting is this kind of missing mesoscale subgrid closure as a function of time. So this is days down here. The truth, which is directly calculated from the simulation, is in blue. The orange is our prediction. And the green lines are the 95% confidence interval that we calculated from the standard deviation. And so what you can see that is overall, the prediction is always within those kind of 95 confidence interval that we've chosen. So it's kind of a nice way to have some uncertainty quantification in our prediction, associated with the neural net. So it's one approach, but I always believe that when you make a prediction, having an error bar associated with it, even though it might not be perfect, the true error is still something important. So that's one step towards this. Another thing that we've been doing, and that's led by Jem, who is a PhD student at NYU with us, is we took some images, right, for the neural net as input. Did we need such wide stencils, and can we get away with less? Or basically, in other words, where is the information content comes from? And so what Jem did, tried to do a little sensitivity to the field of view of the CNN. So basically changing the size of the input, the size of the images that we're using, and looking at, our metric of R squares actually decreasing. And so here, this is R squares as a function of latitude. So latitude is basically meridional direction, so north, south. And each one of the line is R squared for a different input size box. And so it's kind of a way to show us at which point the scale is decreasing depending on the input size, meaning how non-local do we need to be when we build those turbulence closure. There is some non-locality associated with it, but it's not as wide as one could think. And so here for the momentum, we basically find some kind of threshold and an input box that is about 7 by 7, right? On the coarse grid. So I mean, we still need about, kind of a few grid boxes over which, a drastic change will happen. For the temperature, if we are learning the subgrid temperature forcing, so a bit different, then the cutoff is different. So now in terms of locality versus non-locality, the gradient is sharper. And it's usually associated with the physics. It's associated with the scales that you need as input to understand how the turbulence will form, basically. And so here's just another way to visualize that, is that we start losing information as we decay away from a few grid box size from the center over which we took the input. So it's a way to kind of try to understand a little bit, how local versus non-local our parameterization need to be. And here overall is we do need some non-locality, but it's not crazy. We don't need to, go all that far out. And that's helpful actually when we do implementation. And that's what I'm going to talk about right now. So we learn those kind of turbulence closure from data, but at the end of the day, I need to plug them back into a coarser resolution simulation. So what I need to do is to take my coarse resolution equation. So the bar, I mean, I'm on a coarse grid. And now I'm going to need to add my turbulence closure that I just estimated directly from data. And in this case, what we've done is we took a quite idealized simulation, mostly because it makes our life easier. And I'll tell you in a second why. And what we've done is in that idealized simulation, we did not retrain our CNN, right? We didn't retrain our convolutional neural network. We simply took the input surface velocity from our new simulation, fed them through the neural net, so get a mean out of it. And for the standard deviation, we basically multiply it by, again, some white noise. So our full estimate is the mean plus white noise times the standard deviation. So we're basically sampling from the probability of the subgrid forcing that we just learned. And so of course, because you have something that is, stochastic in quote, you can run ensembles. So here I'm just plotting 3 members of that ensemble. And what I'm showing is the kinetic energy as a function of time. So down there is days. The low resolution does not have much energy, right? Without any closure, without any turbulence. Now the high resolution is the pink line, the violet line. And so more energy. If I take the low resolution and then add our neural net closure, again, any of the ensemble that we pick, the amount of energy is higher. So what we've done is we energize the flow, and we also energize the inverse cascade, right? This idea of taking energy from the small scale and feeding it into the large scale flow. So there's some success here, which is always a plus, but the challenge was I could only do that in a very idealized simulation and in Python. And why? Is because actually our climate models are in Fortran. So, usually that horrifies a lot of people. So, climate models have been, written for quite some times now, and they're very efficient on explicit computing, and the interfacing between the machine learning in Python and the climate model code in Fortran is non-trivial. So now there are quite a few solutions coming out there, and so we're implementing our neural nets into climate models as we're going along, but definitely require some some work there. So I'm not going to talk so much about this simply because this is outside my area of expertise, I would say. But there are definitely a lot of efforts trying to kind of do that interfacing in an efficient way. Parallel computing is also not the easiest thing when you're trying to implement CNN. And I think that was asked before. Grid cells are communicating to one another. And so when you actually do that in parallel, and you need to actually break your model into pieces, there's some kind of connection between 2 different cores. So so you do need that connection when you're running on 2 cores, or basically 2 processors. You need to exchange information. And so if you have a very wide stencil in your CNN, that means you need to keep more information and you need to do more back and forth, and that makes the computation non-trivial, or basically more expensive. The last challenge with deep learning, so the 2 first bullet points were kind of a little bit technical, but the third one for me is, I'm a physicist. So, however you want to call it, interpretability or explainability is something that, we're missing. So we did a little bit of sensitivity, and you can do a lot of method with deep learning, but it's really hard to figure out what we really learned. And, are we over-interpreting what we have? So the second part, what I'm going to talk about is a little bit more about equation discovery and trying to actually learn new physics. So I'm going to pause for a second if there are any questions before I move on.
There is one comment. Would be interesting to see what features the CNN learns.
Yes, so yeah, we definitely looked at all of this. So activation functions, features. So usually the first layer, you can figure out that it's learning the first derivative. And then after that, it's a whole scramble because the scale interaction is just so vast and it's really difficult to actually interpret most of what we're learning. But I'm going to show you some trick that we're doing in a few slides to actually try to rethink a little bit what we could get out of the neural net in a maybe more interpretable way.
Then a question from Bob, when you say data, you mean high resolution model results,
Yes.
not actual observations?
Yeah, that's an excellent point, yes. And so as I mentioned earlier, we've been using high resolution simulations, the ones that we have, and I'm going to come back again to the data quality towards the end. And this is definitely one of the big challenges, and so I'll bring this back.
And then maybe one last question before we continue from Daniel. How does the CNN stencil size compare to the numerical stencil of the simulation?
Yeah, so it's much wider, obviously, right? So I mean, the stencil of the numerical simulation, you know, I mean, you can think about, you know, whatever numerical scheme you're going to pick, you're going to, you know, you're going to need some connection, you know, up to, if you're using a Laplacian or something like this, just, you know, basically a few grid boxes. Here we went all the way to 20 or something like that. So we, you know, much wider than just a simple, you know, first or second derivative stencil on whatever numerics of the model we're using. But it was not necessary. So again, I'll come back to that.
Okay, we just got another question. Let's just ask this one and then continue. So from
Sounds
Steve,
great.
what inputs are given to the CNN? Is it just the primary variables, velocity, density, temperature, or does it depend on other quantities like location or depth?
Yeah, excellent question. So we've done about 1 million tests. So initially we only give main quantities, so basically main variables, so velocities. We've added temperature and things like this. We do not give location because it's not great to give location, right? Because that makes it a little bit unphysical because a PDE does not necessarily know location. But now we've added additional features which actually have some embedded location in them. Because when you give a wider stencil with temperature, for example, then actually, because of the way the gradients are set up, there is embedded you know, information about location without being implicit. We've added things like vorticity, which is the curl of the velocity, for example, so not a direct, you know, variable of the model, but a key physical quantity. So we try to stay away from any geolocation, you know, explicitly. Great, good. Is that okay for me to move on?
Yeah, let's move on.
Perfect, great. So I'm going to show you a few slides now about interpretability and you know, how to actually maybe learn something. So this, I mean, again, you know, I think I mentioned it to Steve before. This was very much inspired by, you know, some of the papers on CND about learning equation directly from data. So here, what we wanted to do is rather than learn, you know, the full PDE, you know, of a system, we wanted to learn only the closure. So again, all we're doing now is learning the subgrid tendency or the subgrid closure for that ocean turbulence process that we're looking at. So the input are still going to be basically, you know, data from high resolution simulations. We're going to give the algorithm a set of basis functions. So here, those are actually physical quantities. So it's the divergence of the fluid, the vorticity, and what we call shearing and deformation. So they're all related to turbulent processes and how scale interact with one another. And then we construct a library of function based on this. And so we used a relevance vector machine algorithm, which is basically a sparse linear regression, right? So all we're going to do is we're going to go through that library of function that we only wrote as function that could be written as the divergence of a flux. That means we conserve momentum in what we're doing. So we're kind of trying to remain faithful to the physics and let the algorithm basically prune the library of function. And so we're going to select a few of the functions that, you know, they basically mimic the best the subgrid turbulence forcing that we're after. And each one of the weights, you know, is a Gaussian weight because it's a Gaussian sparse algorithm. So here's one of the equation we discover, you know, for ocean turbulence. It's kind of nice symmetric stress tensor, even though we didn't ask the algorithm to learn something that was, you know, symmetric, which is great. Kind of, you know, kept some of the physics in mind. And we were able to interpret actually that expression. We're able to relate it, to some earlier work, some by others and some by ourselves as well, trying to actually understand how the fluid elements actually interact with one another and how they re-inject momentum and energy into the flow. So we're able to explain about 70% of the variance with an expression that I can write down mathematically and I can go and interpret. And so that was pretty exciting for us, obviously, because now we have something that, it's an equation, so I can go and learn from it, again, without any a priori. Now, what happens if you actually try to plug that into an idealized model, right? So as I said before, we're only doing it in idealized simulations. Well, the first thing that happened, it just blew up, right? So I put tuned in kind of, large fonts here, is that when we put this kind of newly discovered equation, the model was numerically unstable. We also tried to compare it to a neural net in which we constrained momentum. So we built within the architecture a conservation of momentum, and the model blew up as well. So numerical instability, even if you sometimes impose constraints, when you couple it to a coarser resolution model, is still, you still can have issues. And I think that's one of the big challenges that still remains, is that how do we actually remain faithful to the coarse resolution model in which we're going to implement the parameterization? And so that's, that's still one of the big deals. So what we've done is we tune it down, right? So we basically had a little fudge factor in front of each one of the parameterization, and we run the simulations. So again, kinetic energy as a function of time. Low resolution is this, gray line over here. High resolution is the cyan up here. And the equation discovery are, those lines over here. And the violet curve is the low resolution with the neural net. So neural net is a little bit superior to, at least in this metric, than the equation discovery, but on other metrics, they're actually equivalent. So again, it's kind of, a little bit of, pros and cons here, is that the neural net, even with embedded conservation, needed tuning. It does marginally better, but I couldn't quite interpret anything that I got out of it. The equation discovery, a little bit less skill, but still pretty good, even though it's tuned, especially on many other metrics, but it's something that I could understand. So, it depends a little bit what you're after. High skill and high performance, which sometimes can be marginal, versus interpretability. And so, of course, as a physicist, I go with interpretability a little bit more, but nonetheless, I still haven't given up on neural nets. Now, the challenges, right? So I showed you something where I could understand the answer. When we did the same game in Courant, where we tried to learn a parameterization, but now rather than learning it for momentum or velocity, we learned it for buoyancy, so meaning temperature, if you want. Still ended up with a new term. Could explain 50% of the variance with only just a few terms, and so again using idealized, high resolution simulation. But the term that we got, we couldn't interpret it. Actually, it didn't even depend on buoyancy gradients, which was a little bit puzzling for me, I have to admit, when we give it, some of the library of function being function of the temperature gradient or the temperature itself. So I found that a little bit puzzling. So of course, after a little math and a little physics, we're able to kind of, make a few assumptions about the physics and rewrite it in something that looks, reasonable and that makes sense physically, but I was only after we could go and play with the equations, and we couldn't still get it directly from the algorithm itself. And so here, you could put that as a challenge. How much do we need to tweak the data, or how much work do we need to do after the fact to make it into something that is truly physics and interpretable? And so that's a little bit of a question mark, right? Of course, we can't ask the algorithm everything, but it still means that, some knowledge is required and some knowledge is needed. So as I said, we've learned some things, and now I'm kind of joking about this a little bit. It's kind of a backward propagation of knowledge. So we've done a lot of things by using, complicated climate model data, idealized model data, a bunch of different methods, and we find pros and cons in each one. But we haven't done something that was extensive within one framework, and so we're going back and trying to rethink within one given framework, to try to actually, capture our main goals as physicists, which is one, we want to aid in physical mechanism and their interpretation. That's really what we're trying to do here when we try to understand and model the climate. We want our method to be actually robust, right? We want our results to be robust and be interpretable. And want to ensure that we validate them and we can verify them, and we have some uncertainty quantification. So we've been kind of playing within a framework of quasi-geostrophic turbulence, which is kind of a pretty big approximation in our field, kind of capture this kind of mesoscale interaction. And we're rethinking a little bit all of those methods that I told you about, how to diagnose the data, when you have noisy data, when you have less data, what kind of network should you learn, how to use different, symbolic regression type methods. So really trying to redo everything within that framework and then doing the online implementation directly within that framework. So the model is already online, has been basically kind of, put together by some of our colleagues long before us, but it's great because it's easy to implement, and very soon, hopefully, all of our data sets and metrics and machine learning models will be up on GitHub. So, basically in 2 or 3 weeks, everything should be up. But so rather than bore you and show you all the same thing all over again, I'll show you a few new things. Then, in addition to some of the earlier method that I showed you that we're trying out within this framework. So one of them is trying to mix up equation discovery and neural net. And that goes back to some of the question about, which features did you learn? So here what we're doing, and this is work led by Andrew Ross, was a postdoc with us, graduated from computer science from Harvard just a few months ago and kind of joined our group. So what he's doing there is to actually train a neural network with some basis functions directly as input, and then estimate the importance of the output to input gradients using a Taylor decomposition of first and second derivative, and literally kind of extracting the most important term based on that decomposition. And then repeat that procedure all over again to build a new model based on those most important basis function combination. And you can repeat that. And there is some efficiency to that. And some of the results that we get is, one, it's a little bit more scalable than kind of baseline symbolic regression, because you don't need to pre-compute all the possible combinations. You only go with the ones that basically your first path of neural net does. The models that we're learning within that framework, within that particular case, are actually, pretty similar to the one you would do with symbolic regression directly. And it transfers slightly better. Again, it's within one configuration. So again, more tests to do. And again, this could be kind of a nice way to mix up, this kind of deep learning, ability, to basically capture a lot of information without having to pre-process all the input functions. So kind of finding that search, basically narrowing the search space by doing a combination between the two. And I know, again, your group has been working a lot on those ideas, how to find the best latent space or kind of the sparse coordinates. So it's kind of a slightly different flavor of this. Another idea, and that's work led by Ziwei Li, who is also a postdoc in our group and also started a few months ago, which is trying to take into account the fact that we are solving everything onto a stencil, meaning that the way we discretize the equation is important. So here is still learning a subgrid tendency parameterization for those kind of mesoscalities, but it's taking into account the fact that we are on the grid, on a stencil, and what it's doing is basically learning polynomial terms for basically those kind of, for this grid, right? And so again, we're thinking about U and V here only, and what it's learning is basically learning linear, quadratic, higher order kind of polynomial terms to output only the flux that is within the divergence here. So basically only the stress tensor for the turbulent term. So that's pretty efficient because you're already on the grid. So you're not going to have any problem of, approximating additional derivative and so on. You're only learning on the stencil for a polynomial. So again, very preliminary results, but what it's finding is that, again, it's kind of what we call polynet, so polynomial and stencil. Does a pretty good job at inverse cascade. So again, kind of, mimicking this effect of turbulence onto the large scale flow. And what it's trying to do right now is trying to think a little bit about how to rewrite this so that it can embed some constraints. So right now, the polynomial does not have any, conservation of energy, which could be problematic. So it's something that we could impose, and this is something that is working on. So now it's a slightly different way to kind of do equation discovery, but, really thinking about the coarse resolution grid on which you're going to implement your equation, but also in a very simple way. Okay, So I'm going to conclude the next couple of slides, and hopefully there's plenty of time for questions. So I'm a big believer of bringing physics data, for climate modeling. I think there are many ways to do it. I think at the end of the day, it doesn't really matter, how much computing we're going to get for the next few years. We're still going to need closures. We're still going to need parameterization to resolve many of those processes. Every time we increase resolution, there's still more processes we're not resolving. So if we want to improve our simulations and climate projections in general, again, parameterization will remain in demand. In addition, or at least for me, I also feel like I learned something about scale interaction when I look at data. It's something we didn't have before. So even if those are high resolution simulations that are imperfect, there's still new physics that, again, we were not able to simulate before and not able to actually, visualize before. And so understanding that is actually pretty critical. And that's where I feel, again, kind of, machine learning can help us here. So I showed you kind of, two sides of a coin. Deep learning can be great, high scale, super high R squared. I showed you it generalizes. Actually, it's also transferable. I didn't show you that, but we've done plenty of tests. Interpretability is a little bit difficult. So we find ways, but it's still non-trivial and still remains a little bit hard. Equation discovery can be great, highly interpretable, generalizable, super flexible for implementation. I forgot to mention that. I mean, you have an equation, so you basically kind of discretize it on the stencil that you have within the numerics, so highly transferable without any problem here. And you can discover new things, right? So that's super exciting. Now, sometimes you might not discover anything new. You might still learn some noise, but I'm going to come back to it in a second. So there's still many challenges and opportunity ahead, right? So I think for me, challenge equal opportunity. So it's kind of cool and still exciting. We still need to find this kind of perfect optimal blend between physics data and machine learning. I show you some example where even though within the network you have a physical constraint, still the numerics will blow up. So you're still a little bit stuck sometimes. So we need to find this kind of perfect combo. And I think that means also a lot of trial and error, but making sure we take a step back and try to think about the bigger picture in an environment where we can control many of those issues and problems as we move forward into climate modeling. Learning. So defining correct metric for learning seems a little bit boring, but it's actually pretty important. On some metrics we do well, on others we do poorly. Data quality, and so that was brought up. So far, I only told you about high resolution simulations, but they're imperfect, right? So there's still numerics. Observations for the ocean, it's pretty hard because even though we increase them, the amount of data that we have and the noise associated with it and the sparsity is still a bit of an issue. So, how are we going to play, between really real observations, but less of it, and model data, something to think about. And of course, are we learning physics or are we learning noise? And that will always remain the question. And I think that's always important to keep in mind. Doesn't matter how high your R square is, we still need to figure out that we're learning something that is useful. Implementation in climate model, I told you, tuning can be an issue. Having some uncertainty quantification, I think, is important for everything in general. Having a good scale score is not as important as having a good error bar around it, I would say. And of course, here I showed you a lot of idealized simulations, but are we really truly going to improve global simulation? And that's exciting because a lot of the old problems are still here. We have some new problems, but something to think about. And it's pretty exciting. Again, we have great support from Schmidt Futures, where we're actually trying all those concepts, how to use data, physics, and machine learning to improve climate models, to improve the scale of climate models by learning subgrid closures for atmosphere processes, ocean processes, and sea ice processes. So really kind of cloud, vertical mixing, the kind of ocean turbulence I told you about, but also smaller scale, the interaction between the ice and the atmosphere. And so we have 3 climate modeling centers, 9 institutions in the US and in France. So there are 30 of us, from climate model developers to domain scientists to machine learning experts, with lots of early career scientists kind of working on this exciting topic of how to bring data, physics, machine learning to improve climate models. So thanks again, everyone, and I'm looking forward for more questions.
Awesome. Thank you so much. This was really exciting work. We have a couple of questions in the chat. Maybe I just start reading them, and then I suggest people can raise their hand and we can maybe have a discussion. That's probably more exciting than just me reading the chat. Okay, so the first question from Daniel: when the simulation blows up from the RVM closure, is it wave mode dependent, as in more growth in low frequency versus high frequency, or vice versa?
Excellent question. So in the RVM, what we found is that, so basically what we're doing is we putting a little bit too much what we call entropy, so a little bit too much noise at a small scale, and it basically keeps aggregating. And so that's really where the instabilities come from. In the neural net, it seems to be different, but we're still a little bit struggling to figure out where the instabilities are coming from. But yeah, great questions.
Then a short one from Bob: basic equations solved by finite difference or pseudospectral?
Yes, okay, so in the first part of the talk, so everything was basically on discrete grid. For the new kind of test bed that we're using, it's pseudospectral. But in general, an ocean model will not be pseudospectral because we've got boundaries everywhere.
Then we have a really long question from Lucian. Maybe you can just raise your hand and then I can unmute so that we can have a small discussion around this question. Lucian, if you are here, yep, unmute. There you go. Oh no.
Hello, thank you very much for this very entertaining presentation. The point that I was trying to make, pretty much it seems to me that you are taking, to a large extent, sort of an LES approach, like a larger dissimulation approach in which you might have a subgrid scale model, but now you are trying to come up with a closure model in that context. And my point, the other point that or what I've seen based on the results that you presented, it seems that they are based on spherical grids. And in that context, you have the mesh resolution is quite, it has quite a lot of variations. So the results at the poles are way better resolved than what you have at in the equator regions. And in that context, what I see is that obviously, if you are gonna, like the stencil that you apply, it covers a different area, right? You're gonna take a certain number of cells. So it's gonna be quite in terms of the domain that you cover for the machine learning part, you cover different swaths of domains, right?
Yeah,
and
absolutely.
So I'm trying to say, okay, at which scale this becomes a valid approach where it breaks down? And the idea is, can you actually get sort of, if you want, like an order of convergence sort of approach in which actually you can say, hey, don't even bother, or actually this is the minimum scale that you would need.
Yeah, so I can answer that. So there were a couple of points. So yes, we are on a spherical grid, right? So I mean, it's not exactly spherical, it's tripolar, but so be it. So what you mentioned is, are things much better resolved at high latitude? Actually, it's unfortunately not correct. Simply because the scales are getting finer at higher latitude, again, because we're on a sphere, on a rotating sphere. So actually we resolving turbulence less well when we go to high latitudes. So that's one point. The second point which you mentioned is, of course, we keep the same box size if you wish, and we're trying to resolve or we're trying to learn the closure from the same kind of stencil, from the same input size, sorry. So we've done actually a lot of sensitivity to that. So, how much do you coarse grain, what the size of the coarse graining you need to do, for which, it will break and where it won't break. And it will depend heavily on what we call the deformation scale, which is basically where you actually resolve or don't resolve the mesoscale. And then again, how blurry your images are. So we do have actually a whole sway of sensitivity results for that. So it depends both on the physics and on the grid that you have.
Thank you.
We have one question from Prakash in the chat. Or if you want to ask it yourself, you can just raise your hand, but I don't see it. So some of the R-square metrics you mentioned, are they on the QOIs or the model terms themselves? Having a good score in the latter doesn't necessarily mean a good score in the former, at least in a standard LES context.
Yeah, absolutely. Excellent point. Yeah, offline, online metrics, wide differences. So I showed you R-square when it was basically offline. Then after that, basically the kinetic energy were fully online, where the closure was implemented directly. And again, depending on the metrics that you pick, you do better or worse. But offline metrics surely does not translate into online performance, as I showed. Well, it's not always. Sometimes it does, but it's not obvious it will.
Are there any other question? It's 1 p.m., but maybe if someone has a last question, we could ask that. Just raise your hand or type it in the chat. So from Lucian again, why not using cubed sphere grids?
Yeah, so some simulation do use cube spheres, some use tripolar. I think it depends on the modeling center. There are multiple reasons for using one grid versus another. So some modeling centers do use cube sphere.
Perfect. Right. There is another short one from Lucian. What about AMR?
I'll need what's the acronym here?
I unmute Lucian so that he can maybe ask a question himself.
It would be about adaptive mesh refinement. What happens
adaptive
when you
mesh? Sorry, yeah. So adaptive mesh, that's a whole other story. So some regional models are adaptive. Some centers are using adaptive mesh, but it's still pretty rare. I think that's another step, I would say.
Awesome. Yeah, thank you so much for that really exciting talk. Thanks for being here. And yeah, I guess we can close here, as we heard a lot about closures, and see you guys in probably 2 or 3 weeks for the next talk.
Thanks again. That was great. Thanks all for having me.
Bye.
That was awesome. Thanks, Laure.
Thanks, Steve. Thanks, Nathan. Thanks, Urban.